Do you know how mathematicians can predict function values without calculating them exactly? Do you know why some approximations work perfectly while others fail? What about power series? Do they always give accurate results? In this video, we are from Group 1 present our poster entitled Convergence and Accuracy of Power Series Approximations. Through graphs, comparisons, and error tables, we explore how convergence affects accuracy and why it really matters. Let's get started. Now, in this poster, discuss how power series are used to represent and approximate functions, as well as how their convergence affects the accuracy of those approximations. The first one, we begin with an introduction. Introduction that explain the basic concept of power series, the idea of radius of convergence, and their importance in mathematical analysis. Next, we present the objectives. The objectives of this study, which include understanding power series as function representations, determining their interval of convergence, and using them to approximate function values. Next, in the methodology section, the poster outline the steps of our analysis starting from determining the power series of several functions, identifying their intervals of convergence, creating comparison graphs, and analyzing approximation errors. And then the results section. The results section contains visual graphs of rational, arctangent, and natural functions along with their power series approximations. Their graphs help illustrate how the accuracy improves as more terms are included. Additionally, the poster provides error tables. The error tables which numerically show the difference between the actual function values and their power series approximations across different intervals. Finally, the conclusion summarizes the key finding. The conclusion emphasizing that the accuracy of power series approximations depends on the radius of convergence, the number of terms used, and the chosen evaluation point. Through this poster, we aim to give a clear visual and conceptual understanding of the convergence and accuracy of power series approximations.
Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. Welcome to today's project presentation for the multivariable calculus course. It's a pleasure to have you all here. First and foremost, we would like to express our deepest respect and gratitude to our esteemed lecturer, Dr. Annelies MSE, Your guidance, support, and invaluable insight have been instrumental in the completion of this project. Thank you for being such a wonderful mentor. Today, we will present our project titled Convergence and Accuracy of Power Series Approximation. This project explores how infinite polynomial series, known as power series, can represent complex functions and investigate the condition under which this representation remain accurate and mathematically valid. Next slide, please. Next, allow me to introduce the member of Group 1. Each member will briefly introduce themselves. First is myself, Aisyah Soleha with student ID 240299049.
My name is Alia Azra Fadia with student number ID 240295052.
My name is Elsha Sarisahari with student identity number 24029011.
My name is Irshad Kamil with student ID 24029016.
And I am Jorge Abdillah with student ID 240290021.
Together, we're from Group 1 and we're excited to share our research for our project. First, we will begin with the first section, background of the project. Let's understand why power series are such an important topic in calculus and applied mathematics. Let's welcome the first presenter.
Now, I would like to explain the background of this project. First, the main problem addressed in this project is that many functions in calculus and differential equations are difficult to represent, analyze, and compute using simple algebraic or polynomial methods. As a result, these traditional approaches are often insufficient when dealing with more complex functions. Second, this problem arises because polynomials contain only finitely many terms, which limits their ability to model complex functional behavior. When infinite series are introduced as an alternative, new challenges appear, particularly related to convergence, which must be carefully analyzed. Third, the effects of this problem include difficulties in accurately approximating function values, analyzing derivatives and integrals, and solving differential equations. Without an appropriate mathematical framework, this task can become unreliable or inefficient. To address this issue, power series are proposed as a solution. Power series allow functions to be expressed as infinite sums of polynomial terms and make it possible to determine the intervals of convergence. This solution is chosen because power series provide a clear convergence framework, support term-by-term differentiation and integration, and are highly effective for function approximation and mathematical analysis. Therefore, this project focuses on the use of power series as a powerful tool for representing and analyzing complex functions in calculus.
Thank you. That gives us a clear context for our study. Next, we will move to the theoretical foundation, where we'll define what power series are and explain their mathematical properties. To next presenter, time is yours.
Hello everyone. Today, I would like to explain the theoretical foundation of power series. First of all, what is power series? A power series is an infinite series that has the general form the sum from n equals 0 to infinity of a sub n of an times x minus c to the power of n. In this expression, we know that an are constants called coefficients, and then x is the variable, and then c is the center of the series. This means that a power series is built from powers of x minus c, starting from power 0 and continuing infinitely. Next, if we write the power series in expanded form, it becomes a0 plus a1 times x minus c plus a2 times x minus c squared, and so on. This form help us see how the series is constructed term by term. A series of this form is called a power series in x minus c. Everything we study about power series in x also applies to power series in x minus c. Now, let's talk about the convergence. The convergence, which is a very important concept. A power series does not always converge for all values of x. Instead, the set of values where the series converges is called the convergence set. There are three possible types of convergence sets. The first one is a single point when x equals c. This means the series only converges at its center only. The second is an interval, the open interval from c minus r to c plus r, possibly including one or both endpoints. R is called the radius of the convergence. And then the last one is the entire real line atau the whole real line uh, meaning the series converges for all of the real values of x. As shown in this picture, the convergence interval, the open interval from c minus r to c plus r is centered at c, with distance r to the left and right. This visual representation helps us to understand how far the series converges around its center. That's all from me. Thank you for your attention. I give it back to moderator.
Thank you. Now we proceed to the core of our presentation, the research findings. We will analyze three distinct functions to observe how power series behave in different scenarios. To next presenter, time is yours.
Okay, I'm M. Jorgadila, will explain the result finding. Okay, the first one is the rational function. Here we can see the original graph of the rational function. The rational function can be expressed as the terms of a power series, as shown in the slide. From the power series, we will compare the graph of the original function and the approximation graph using the first three terms of the power series, then the first five terms of the power series, and finally the first 10 terms of the power series. Let's look at the next slide. Okay, we can see that the power series approximation of the rational function is accurate for the region around 0. And as we move away from 0, the graph becomes very steep and very far from the power series approximation from the original function value. Next, look at the error table. In the power series approximation table, here we can see that the accuracy of the approximation values is only around 0 to 1 and 2 and 0 to -1. And at the endpoints 1 and -1, the graph becomes steep and shows inaccuracy in the values. Next, is this the arctangent function. Here we can see the original graph of the arctangent function. Arctangent function can be expressed as terms of a power series, as shown in the slide. We can see that the resulting series is an alternating series, and we know that terms with alternating series and following the harmonic series form can be said to be conditionally convergent power series. Next, we will see how the power series graph compares to the original function graph. We can see that the graph looks almost identical from the first three terms and only change significantly at the end. Next, we look at the error table. And indeed, for the power series approximation, the error is quite significant at the end of the radius convergence. Okay, next. And finally, we move on the natural exponential function. The original graph of the natural exponential function can be seen on this slide. Next, the natural exponential can be expressed as a power series, as shown on this slide. Next, we look at the approximation graph of the power series against the natural exponential function in various approaches to the number of terms. It can be seen that more terms used, for the closer it will be to the original function value. For the first 10 terms of the power series, it is already very close to the original function and overlaps with each other. Next, we look at the error table. For the use of terms, we can see that the more terms used, the less error there is in approximation the original function value. Okay, that's all from me, and back to the moderator.
Thank you. Now we already seen the result for the all three function. We will now move to the discussion section, where we will compare and interpret these findings. To next presenter, time is yours.
Okay, now let's look at the discussion for our first function, the rational function. First, regarding the theoretical consistency, our calculation shows that the radius of convergence is r equals to 1. This means the series is only valid and reliable within the interval of minus 1 to 1. The graphical analysis confirms that as we increase the number of terms from n equals to 3 to n equals to 10, the power series curve aligns more closely with the actual function. However, we observe a critical point regarding error and proximity. The approximation is highly accurate when the evaluation point is near the center, which is x equal to 0. But as we move further away or approach the boundaries of the interval, the error increases significantly and the approximation becomes less reliable. Moving on to the arctangen function. The convergence property here are similar to the rational function, where the series converges only for the absolute x less than 1. In terms of visual representation, our simulation shows that adding more terms allows the approximation to follow the curve of the arctan function more precisely. It's clear that more terms equals better fit, but only within its valid range. Our accuracy observation also shows that the smallest error is constantly found at the center, x equal to 0. Once we go beyond the radius of convergence, meaning the absolute x is greater than 1, the power series completely fails to represent the function, regardless of how many terms we add. Next slide, please. Okay, lastly, let's discuss the exponential function, which is perhaps the most interesting case in our project. Unlike the previous two functions, a to the power of x has infinite radius of convergence. This is a huge advantage because it means the series theoretically valid for all real numbers. Our results show high performance across a much wider domain compared to the other functions. Visually, the power series is very effective at mimicking the exponential curve. However, we did notice a trade-off regarding error growth. Even though it converges everywhere, as the evaluation points move further away from the center, we need a significantly higher number of terms to maintain a low level of error. It is proof that while error is infinite, the number of terms still plays a vital role in a practical applications. That's all for me. I give it back to the moderator.
Thank you. Now we're moving on to the final part of our presentation. After conducting our analysis and simulation, we have reached several key findings regarding power series approximation. Based on our project, we have identified three essential factors that determine the success and accuracy of a power series approximation. First, the radius of convergence. It is crucial to understand that a power series is only mathematically valid and reliable within a specific interval. Second, the number of terms. As demonstrated in our results, there is a direct correlation between the number of terms used and the precision of the output. Simply put, adding more terms leads to higher accuracy. Third, the evaluation point. The proximity of the point we are evaluating to the center of expansion significantly affect the reliability of the approximation. Now, after the conclusion, now we came to the end of our presentation. This is several references that we use in these projects. Next. Now we come to the end of our presentation. We would like to once again express our sincere gratitude to Dr. Annalise MSE for her continued support and guidance throughout this project. We also thank to all of you for attention and participation today. And I also apologize for all the group mistake. To close this presentation, I would like to say Assalamualaikum warahmatullahi wabarakatuh.